And I'm live for all the people in attendance. We're missing, how many people are we missing today? We're missing like 3 people. 1, 2, 3, 4. We're missing 4 people. Yeah. They're probably right there. They just woke up from playing their video games. That's what Destiny told me. She told me that you guys are up late playing video games, so you can blame her. They said they don't like you. Anyway. Yeah, they're probably. Anyway. So, Monday was a fun day. Obviously, on Monday, all of Google went down except for the search bar. And yeah, I wasn't able to do exactly what I wanted to do. I had to improvise a little bit. So technically, and I want you guys to pay close attention to this, technically, I'm in the middle of teaching 2 lessons that I wasn't able to finish because the whole Google thing went down. I wanted to originally finish on Monday a problem that we started the previous Thursday, which I'm going to review with you in the first part of this class now. And then I was going to transition back into poker. But what ends up happening is, well, Google goes down. I don't want to have to teach that particular concept and then have to reteach it, especially for those who are virtual, because, again, I want them to have the same information. So here's where we're at. We're back virtual. Everything should be working, and here we are. So what I'm going to ask is this. For those of you that are here, it was last Thursday. I know it's been a while, but Monday screwed up on me. Last Thursday, I believe I gave you all this particular worksheet. See if you can dig that out. See if you can dig that out. I do have extra copies, though, if need be. I got you. Now, for those of you that are in the chat, I am going to go into the Google Classroom because I had posted last week. There it is. I had posted the PDF of this particular assignment so that you could follow along with what we're doing instead of having to strain your eyes at the board. So for those of you that are in the live stream right now, in the chat, I just posted the Google Classroom link that should take you, and I'm double checking it right now, but it should take you to the link. Yep, there it is, with the PDF of the problem that I specifically want to look at. So if you're in the chat, open up that PDF if you haven't already. And obviously, if you're here, you got this particular problem in front of us. The problem in question was number 3. This is what we started last Thursday. We ran out of time. I was supposed to do it on Monday, but Google messed up. So here we are. So I'm going to change over my screen. Let's see here. Come on, screen. I'm going to change over my screen. Click. There we go. I'm going to bring this problem up, and we're going to pick up where we left off. Let me just recap a little bit of what's going on here. In this particular problem, they were trying to figure out the probability of a randomly selected humanities major being a junior. Now, I believe, actually, if I go back to my notes from that particular class period, yep, there it is. If I go back to my notes from that particular class period, I wrote down the following probabilities. Hold on. There it is. So if you, I'm going to move this because I need this to be right here. There we go. Cool. But if you don't have these probabilities written down, which obviously we put them into our notes last Thursday, but if you don't have these probabilities right down, I'll leave these up here for a moment and reference the worksheet just to recap exactly what happened. So in the original problem, it says, for the purposes of making budget plans for staffing, a college reviewed students' year in school and area of study. Of the students, 22.5% were seniors, which I did the probability of a senior being 0.225. Juniors and sophomores were 25%, 0.25. And the rest were freshmen, meaning all four of these numbers right here should add up to 100%, which they do because we figured out that there should be 0.275 freshmen. But where it really got interesting was the statement afterwards. And this is where I really had to buckle down on that given statement. It says also 40% of the seniors major in humanities. 40% of the seniors. Given that you are a senior, 40% major in humanities. The probability of majoring in humanities, given that you are a senior, is 40%. That is the structure of that particular probability statement. The following statements after that follow that same rule. 39% of the juniors, 40% of the sophomores, 36% of the freshmen. Given that you are looking just at freshmen, 36% of them are humanities majors. That is where this thing kind of came into play. Now, I'm just going to separate some stuff up here. Come on, marker. Where'd you go? There we go. So I got that. I'm going to separate that. I'm going to separate that. There we go. Structured that a little bit better. Then the question. The question itself really kind of messed it up. What is the probability that a randomly selected humanities major is a junior? That's the question at the bottom. I believe I did write the answer. Did any of you guys write down I wrote it down like the top right part of the board in like dry erase marker last Thursday. I don't know if any of you wrote it down. No? That's all right. That's fine. I wrote it down on the board just as a, hey, this is what the answer is. This is where we're headed. 2523. Hey, he did write it down. There he is. Hold on. Let me write it again. The answer that we're looking for is 0.2523. But the question becomes, how do we get it? See, because none of the numbers. Oh, look, yeah, there. Sorry, she wrote it in the chat too. So I see you there. But none of the numbers written on the board in permanent marker, none of those exemplify what that answer is. None of them. And our job is to figure out how to go about doing that. And that is what I want to do for the first part of this class today. So, if you would, again, if you don't already have them out, I'm going to need those notebooks out and open so we can do this probability tree. We started a little bit of it. We did start a little bit of it. That's why I keep my notes here. Pow. There we go. We did start a little bit of this probability tree last time. And of course, the hope is that you would have this written down already. But of course, if you haven't had it written down, please make sure that you do. And of course, I want to recap very briefly what it is that we did and why we did it. But everything in this probability tree was given to us in the problem itself. So for example, the first branches of this probability tree indicate what grade level you are in. And that is how they're split up. But then the secondary branches are these given statements. Given that you have gone down the senior end of the tree, there's a 40% chance of majoring in humanities. Given that you're already a senior, there's a 60% chance that you would major in something else. Same thing with the sophomores. 25% chance that you're down the sophomore branch. But now, given that you were on the sophomore branch, there's a 40% chance of majoring in humanities. These are all the numbers that were given to us in the problem. But now, that is the question that I had written with a question mark, and I'm going to write that on the board right here. They want to know What is the probability of majoring in humanities? I think I got that backwards, right? It was a junior given humanities. This is the big question. Junior given humanities, which we can't get just by staring at this tree long enough and hoping that the numbers work out. So this is what I'm going to have to add to this thing. Here's what I'm going to have to add to this thing. Move this over here. There we go. Let's come down here. Ha ha ha. Cool. First of all, let me do something here. I have a calculator, and I'm going to do a little calculation here. 0.2. Look what I just wrote down there. I'm going to zoom in just a little bit. Look what I just wrote down there. I wrote down 0.0975. I wrote down 0.0975. How does one get a 0.0975? Look very carefully. I multiplied 0.25 times 0.39. I multiplied those two numbers together. When you multiply probabilities, what is the word that I usually tell you to remember? Was it and or or? When you multiply probabilities, say it again? It's and. Now, that 0.0975 represents the probability, listen very carefully, of being a junior and a humanities major, being both. The word and implies multiplication. By multiplying those two numbers along the branches, I got the probability of being a junior and a humanities major. Now, that's clearly not the answer we're looking for. We're looking for the answer 0.2523. But that is something that we're going to need moving forward. Now, hold on a second. I'm going to write up here 0.09. I wrote 0.09 along this top branch. 0.09, and my marker is pointing to it right now. 0.09 represents the probability of being a senior and a humanities major. I just multiply along the branches. 0.1 is when I multiply 0.25 times 0.4. That got me a 0.1 right there. And a 0.275 times 0.36 gets me 0.099. Now, these numbers are important. These four numbers are important. And I need to know why. These four numbers, okay, the top number, the 0.09, represents probability of being a senior and humanities. This number represents junior and humanities. This number represents sophomore and humanities. This number represents freshman and humanities. Each of those numbers has something in common in terms of the context. Each of those numbers represents something when we add them all together. There's a connection that I need you to make. There's a connection that I need you to make right here. This is senior and humanity, junior and humanity, sophomore and humanity, freshman and humanity. What the heck would happen if I took all those numbers and just combined them? It would give me a very particular probability. Oh no, people. He didn't sleep in. There he is. Woo! Wait, what? There it is. So let me recap what we just did. We wrote down this chart last time. Okay, I'm sorry, let me rephrase. Last Thursday. Last week, or Monday, got messed up because of Google being out. So I had to change my plans a little bit. Okay. but we were working on number 3 right here. You can take that. We're working on number 3 last time. And last time we took all of those numbers from that problem and we organized them into the tree. This is like last Thursday. It's like 6 days ago. Now, what's written in red is the question that they're actually asking, which we don't really have a beat on just yet. What's written in green at the top is the answer. That is the answer, what's written in green. But none of these numbers, none of them represent, obviously, the 0.2523 in green. So the question then becomes, how do we go about doing this? And I'm kind of laying the groundwork as to how we get there. I haven't explained how yet. I have not explained how yet, but we are getting there. We're about a couple steps away. So I added a little bit to my chart. Sorry, I saw a hoodie. I didn't know what it was. I added a little bit to my chart, and I would like, and you guys should have this in your notes from last week, but I would like you to add some of these numbers as well. So what I did was, along this branch right here, along this branch right here, that's the probability of being a senior. This is the probability of being a humanities major, given that you are a senior. I multiplied together along this branch to get this. This is the probability of being a senior and a humanities major, and implies multiplication. This is the probability of being a junior and a humanities major. This is the probability of being a sophomore and a humanities major. This is the probability of being a freshman and a humanities major. Now, why do I need all that? I'm about to add all 4 of these numbers up. What the heck is that going to do? This is when you walked in. What the heck is that going to do if I add up all 4 of those numbers along the side? Will it get me my answer? Well, not exactly. If you add up all 4 of those numbers, I'm going to get another piece of paper. Here we go. If you add up all 4 of those numbers along the side, move this up a little bit. Here we go. 0.09 plus 0.0975 plus 0.1 plus 0.099 gives you 0.3865. That number represents the probability of being a humanities major. Now, clearly, that's not our answer, but that is something that we need, and that is something that you can only get directly from that probability tree. That is something that we will need in order to get our answer. Now I'm going to write something else down here. I'm going to erase what I have in red on the board in a moment, because I'm going to write down this particular calculation. This is a formula that I gave you guys last week. This is a formula that I gave you guys last week. And I'll write it on the board again over here, just so we at least can see it. It was the probability of B given A is equal to the probability of A and B divided by the probability of A. That formula, which of course I would have no problem giving you on any form of an assessment because I give them to the AP Stat class as well. But that formula is what is going to allow us to answer this question. In order to answer the question, junior given humanities, we need the probability of junior and humanities, and we need to divide it by the probability of just humanities. The problem itself does not give you any of that information. You have to dig for it. We just, using this tree, we just figured out the probability of being a humanities major. We did by adding up those 4 numbers. And again, to recap, I got those 4 numbers by multiplying across the tree. Senior N humanities, junior N humanities, sophomore N humanities, freshman N humanities. Then when I add all 4 of them up, that just gives me the probability of being a humanities major. In order to figure out this problem, the bottom of the fraction is that number. What about the top? Do we know the probability of being a junior and a humanities major? Spoiler, we do. What is it? Somewhere on that tree right now is the probability of being a junior and a humanities major. Which number is it? It is the 0.0975. Because, again, going down that tree, being a junior and a humanities major, I multiplied those 2 numbers together to get 0.0975. That is being a junior and a humanities major. Right here, that is the top of the fraction. If you just simply divide those 2 numbers, 0.0975 divided by 0.3865, that gives you the approximate number we were looking for, 0.2523. This is a very involved problem. Knowing how to do a probability tree, which we will have practice on in the coming class periods, of course, but knowing how to do a probability tree is unbelievably helpful when compared to the alternative. And I'm actually trying to look up where the alternative is at the moment, because there actually is a formula outside of the probability tree that I hate. I just want to show it to you. Oh, they don't have it. They're not going to show it to me. Did they take it out of the book? Ugh, that's gross. They might have taken it out of the book here. That's all right. If they took it out of the book, then so be it. But trust me, you don't want to see that formula. I'd rather not learn this gigantic, unbelievably painful formula when I would rather just learn how to do a probability tree. It's kind of nice. I want to try one more. A different problem. So, again, ladies and gentlemen, if you would, I'm going to be asking for this information to be written into your notebooks. But I'm going to get another problem similar to it so that we can do another probability tree problem. There you are. Oh, no, not that one. This one. Yeah, nope. It was this one. Yes, someone get the door. They're showing up. You what? Oh, okay. Let's see. This is page 7. So I'm going to not print, but you'll see. Going to get the PDF of page 7. I'll put that on my desktop for the time being. Oh, yes. I would like to replace that. Cool. And I'm going to throw this into the Google Classroom. Let's see here. So you at least have a copy of what we are referring to. PDF post. Ta-da! Excellent. So for those of you on the screen, now you have a copy of the PDF. For those of you in the class, you can read the problem that's on the board. We'll do one more of these, and then I'll be able to jump to finishing up the poker problems that I wanted to do. A manufacturing firm orders computer chips from 3 different companies. 10% from company A, 20% from company B, 70% from company C. Some of the computer chips that are ordered are defective. Oh no, boo. 4% of the chips from company A are defective. 2% from company B are defective, and 0.5% from company C are defective. A worker at the manufacturing firm discovers that a randomly selected computer chip is defective. Ooh. What is the probability that the computer chip came from company B? Now, again, for those of you in the chat, this PDF of this problem is in the Google Classroom stream, so you don't have to strain your eyes. I sent you the PDF. For those in the classroom, I would like you to draw out the following. So that we are basically on the road to solving this problem. Where did that thing go? Whatever, I don't care. Okay. First, and I'll switch over my camera in a moment. But first, it depends on which company you are coming from. Now, of the computer chips, this is the beginning of the tree that I would draw. 10% of the chips are just coming from company A. 20% of the chips are coming from company B. And 70% of the chips are coming from company C. Yay. Now, of course, I'm not going to leave this chart alone just yet because I have to add more to it. Well, let me go back to the problem real quick. Click. Then it says some of them are defective. In fact, 4% of the chips from company A are defective. 2% from company B are defective. And 0.5%, there we go, from company C are defective. Let me flip back real quick. This is what I just got from the problem. 4% given company A are defective. 2% given company B are defective. And 0.5%, and notice how I wrote that 0.5%, from company C are defective. Now, of course, this tree splits. So I'm also going to fill in the not, just for the sake of argument, because it's always good to have a full tree. Notice I put the 96% up there, because if 4% are defective, 96% are not. If 2% are defective, then 98% are not. And if 0.005% are defective, then 0.995. I'll write that underneath here. There we go. 0.995. There we go. Are not. This is the probability tree that you can get from this problem. I'm going to flip it back to the problem in a moment. But I just want to give you this idea of like, oh, this is how we can fill out a probability tree given this information that they're throwing at us. Now I look at the question. I'll flip back to the tree in a moment. A worker at the company discovers that there's a chip that's defective. Now here's the thing. I want to underline that statement, and I'm going to ask you a question. Hold on. A worker at the firm discovers that the chip is defective. Does he know what company it came from? No, he doesn't. He has absolutely no idea. The only thing he knows is that it's defective, given that it's defective. Hey, I have a chip here that's defective. It belongs in the category of being defective. Of these defective chips, some of them are company A, some of them are company B, some of them are company C. The question is, what is the probability that it came from company B? Let me flip back to my chart, my probability tree real quick, because I want to exemplify this. This is the question that's being asked. Given that it's defective, of the defective chips, what's the probability that it came from company B? Whereas this information that's in the chart right now gave me this information. This is 0.02, this is 0.98. They gave me that information, but now they're changing it up. They're saying, no, I don't care that you're choosing from group B and it could be defective or not. I care that it's defective and now I want to know what company it came from, A, B, or C. That answer is not in the chart right now. The answer is not in the chart right now. Let me write some stuff at the bottom of the page. What they're really asking is the probability of it coming from company B given it was defective. You don't have that information. But the way that we calculate it is we have to find the probability of being B and defective divided by the probability of being defective. This is how we figure out the problem. And the tree is going to get us there. The tree is going to get us there. Where the heck did I get that number from? I just got a number up there, 0.004. Where did I get it? Where did it come from? Why does it exist? I know. I'm sorry. But I got that number from somewhere. If I told you that that was the probability of being B and defective, I'm going to ask the question again, how did I get it? That 0.004 represents the probability of being from company B and being defective. How'd I get it? What operation is implied by the word and? Multiplication. What two numbers did I multiply? Well, that number that the pen is pointing to, 0.004, represents the probability of being from company B and being defective. You just said the word and implies multiplication. What did I multiply? That's exactly what I multiplied. I multiplied those two numbers, the 0.20 and the 0.02, along the branches to get that number. That's why I wrote it on that particular spot. I see you in the chat. She's doing the chat too. So then I am also going to multiply 0.10 and 0.04, which coincidentally give me the same number. And I'm going to multiply 0.7 and 0.005, which give me 0.0035. Now this number, again, this number that I am pointing to, the same number I pointed to before, that number represents being, now look where my hand is pointing right now. Actually, you know what? I'll stand up at the board. I'll stand up at the board because it's more dramatic. That number that the pen is pointing to represents the top of the fraction because it's the probability of being B and defective. The bottom of the fraction. How in the world do I figure out the bottom of the fraction? Adding what up, though? What specifically? Well, these particular numbers, which represent being from company A and defective, company B and defective, company C and defective. Yes, as you just said, you add up those three numbers. All three of these numbers represent defective chips from different companies. If you add them all up, it is flat out the probability of being defective. So the top of this fraction gets you a 0.004. The bottom of this fraction gets you a 0.0115. The final answer is 0.348. If you definitely have a defective chip, there is approximately a 34.8% chance that it came from company A. If it's defective, given that it's defective. Assuming that you are only looking at a defective chip, if you're holding a defective chip in your hand, there's a 34.8% chance it came from company B. That's what this probability allows you to find out. Well, here's the thing, though. There are 3 companies. So it's like if I just had like a random chip, I would assume that, okay, I would hope it's like roughly a 1/3 chance. That's roughly a 1/3 chance, you know? Now, keep in mind, company A actually produces more defective chips than anybody else. But they don't produce as many for like just distribution. They only produce 10% of distribution, but 4% of their chips are defective. 70% of the chips come from company C, but only 0.005% of their chips are defective. I love it. Okay. Like I said, we're going to get a little more practice with this next time. But as I said, you guys, I know a couple of you guys came in a little bit later. But basically, like, obviously, Monday screwed up. That was fun. But I was in the middle of 2 lessons. This was one of the lessons that I wanted to wrap up. The other lesson that I want to wrap up, poker hands. Let's talk about poker hands. So I'm going to set this aside. And recap a little bit of what we did last time with poker hands. We left off, there it is. We left off on something like this. Actually, you know what? I'm going to do it like this. Check this out. I'm going to give you guys a little challenge. Ready? It's going to be amazing. Here's a little challenge for you. You have the items A, B, C, and D. And I'm saying, hey, list out combinations of 2 of them. If you have the letters A, B, C, and D, name 2 of them. No. Name 2 of them. Name 2 of the items. There are 4 items you're given originally, right? You're given the letters A, B, C, D. Name 2 of them. A, B.
A, B, C, D.
Hold on. A, B is one of them. Name another. C, B. Name another one. D, C. Name another one. Well, we have C, B. Technically, C, B, and B, C are the same thing. D, A. Name another one. CA? Name another one. Oh, we have AD. Yep, it's DA. Oh, no. There's one more. DB. Yes, DB. Now, the order doesn't matter. The order doesn't matter. Just like a hand of poker, the order doesn't matter. But those are all of them. And what it comes down to is this calculation that I somewhat introduced to you last time. 4C2. Now, I use different numbers, of course. But what that means is this. If you have 4 items to choose from, and you are only picking 2 of them. Oh, you can't see because of the glare. move that over a little teensy bit. There we go. But if you have 4 items that you're choosing from, in this case, A, B, C, D, and you're only choosing 2 of them, all these choices right here, how many distinct possibilities did we get? We got 6. Let's go to the calculator. Get rid of this. Get rid of this. Let's go to the calculator. We got 6. Now, when I told you there was like 1 left, I felt pretty darn confident. Check this out. Because of the following calculation. Now, again, watch very closely because you have this capability in your graphing calculators. Now, I'm not expecting you to get them out right now because you can see what I'm doing up here, but I want you to see it. If you're going to calculate 4C2, you're going to have to type in the first number. You're going to have to get that combination function. So I'd hit Math. I'd tab over to PRB. And I'd select option 3 in this case, which is NCR. Now, mind you, I'm going to show you this on my... what does that mean? I'm going to show you. I'm going to show you. Trust me. Because last time I just wrote down the beginnings of the formula, but we didn't actually write down what it was. Yeah, because we ran out of time. That's okay. But then I piped in the 2, which represents the number of objects that we were choosing. And again, remind me, how many combinations did we find? No, we didn't. We found 6. Remember? Yeah, here, I'll zoom out. Right there. There they are to the left. Found 6 of them. Now look at my calculator. Chapow. 6 of them. That's what that thing does. That's what that thing does. It's amazing. Now, hold on. Let me flip over here real quick. I want to see what it looks like on the 84. I want to see what it looks like on the 84 calculator. Come on, you. There we go. Second plus sign 7 1 2. There we go. It's all clear. Math. NCR. Oh, sweet. Look at that. On your calculator, I'm going to assume it does something like that, where you put like a 4 and a 2, and it spits out that 6. That's nice. That's nice looking. Kind of nice. Let me go back here. Oh, no. There we go. Let me show you what it is. Because, Andrew, you're like, yeah, but what is it? I'm going to show you what it is. Check this out. NCR equals the following calculation, and then I'm going to give you a definition. It equals the following calculation. N factorial divided by n minus r factorial, r factorial. Look at that calculation in all of its glory. The beauty of it is this. Here's the beauty of it. You're going to be able to use the calculator for it to automatically do that for you. You theoretically should not have to do that by hand. Thankfully. But what it does is this. This calculates, I can spell it, the number of combinations of choosing R items from a group of n items. This is what this does. And I'll show you what I mean in a moment. This calculates the number of combinations of choosing R items from a group of n items. Ha ha ha. It's not actually complicated adding. It's not complicated adding. It's complicated multiplication. So, there are 5 of you in the room right now. I'm just going to choose the 5 of you because you're physically in front of me right now. Yes, I know there's people in the chat and stuff like that, but there's 5 of you here. So there's 5 of you. Now I could give you the letters A, B, C, D or whatever junk like that. A, B, C, D, A, B, C, D, E. Then I might get a call. I might get a call saying, "Hey, Mr. Markey, you need to pick 3 students. You need to pick 3 students. You need to send them down to the office. You're never going to see them again." Oh, that's heavy. Man, this is rough times living in America. So I got to pick 3 of you that I'm never going to see again, ever. You're never going to see anyone else again either. I don't know what's going to happen to you, though. So I have to do this kind of randomly. But the question then becomes, how many different ways can I pick you? How many different ways can I pick you? So I could be like, okay, A, B, C, A, B, D, A, B, E, B, C, D, B, C, E, C, D, E. Did I get them all? I think I did. Oh, no, I totally didn't. You're totally right. I didn't. Oh, my gosh. I could also go A, C, D, A, C, E, A, D, E, B, D, E. How many I got so far? I got 10 so far. Man, I wish I knew if I had them all. I wish there was a way of knowing if there are 5 of you and I have to pick 3 out of the 5. If there was a way of knowing that I got them all. This is where like the infomercial be like, but wait, there is. Because if you go to the calculator and you do 5, choose, and this is the combination choosing calculation right here. 3. Yep. I got all of them. I got all 10. This is how you figure that junk out. This is how you figure that junk out. I know that is rough. So, poker. In poker, there is a way to use this function to figure out exactly how many different ways, how many different combinations there are to get a certain result. And what I would like to do, very simply with you guys, but with the time that we have, I want to calculate the number of ways to get a full house. What's a full house in poker?
Is it a pair of every suit or one of those?
Nope. 3 of a kind, 2 of a kind. That's full house. 3 of a kind, 2 of a kind. So hold on. Full house is 3 of a kind and 2 of a kind. Check this out because we are actually going to calculate the number of different ways you can get a full house from a deck of cards. First of all, let's talk about the 3 of a kind. You could have a 3 of a kind of what? Name one of the 3 of a kinds you could potentially have. You could have 9s. You could have 3 9s, right? Hold on. You could have 3 9s. There's 1. There's 2. I'm going to put this on the screen in a moment. There's my last 9. There's my last 9. Cool. Aha. Check this out. You could have these 3 9s. But watch very carefully. Watch very carefully. You could have these 3 9s. Or, you could have these 3 9s. Or, you could have these 3 9s. See, the thing is, there are multiple ways to get 3 9s. Because how many 9s are you choosing from? There are 4 of them you have to choose from. Question. You could have 3 9s, but you could also have 3 8s. You could also have 3 kings. You could also have 3 aces. How many different kinds of cards are there to choose from? We did write this down like a week and a half ago.
You have
Unfortunately, no, I don't. I know. Not 12, 13. Because you got 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, Ace. There are 13 kinds to choose from. There are 13 kinds to choose from. This chooses the kind. I don't know what kind of card it's going to be, but 13C1 chooses the kind of card. Then, I'll zoom in on this. This chooses the 3 cards. This is what this function does. NCR. The N represents the number of items you are choosing from, and the R represents the number of items that you are choosing. So in the case of these 4 9s right here, there are 4 of them, but in order to get 3 of a kind, I only need to choose 3 of them. I only need to choose 3 of them, but I don't know which 3, and it doesn't matter which 3. But how many different combinations there are does make a difference for figuring out how many different full houses there are. Because I could have everything but the heart, I could have everything but the diamond, I could have everything but the spade. But now I got to pick the 2 of a kind. Now I got to pick the 2 of a kind. Pick a different 2 of a kind. I'll pick it, king. I'm just moving ahead. I'll pick the kings, because they're easy to find. Oh no, unless they're not. Come on, this was a full deck. There you are, little king. Now there are 4 kings. But check this out. To get the 2 of a kind, first I have to pick the kind.
Which one's the real king?
Doesn't matter. Notice what's different about that calculation. What did I change in that second choosing of the kind? What? Yeah, I changed it from 13 to a 12. Do you know why? Kinda. I'm taking a kind of card out. See, in this one right here, there are 13 different kinds of cards to choose from. And I named them all for you. But now here's the thing. Now that I've chosen that kind of card, according to the rules of a full house, I can't choose it again. So in the second choosing of a kind, I have to eliminate one of the kinds because I've already chosen it. So for example, if we got 3 9s, we can't then get 2 more 9s. We can't do it. It's not possible. There's not 5 9s in the deck. 9s now can't be of this choice, and I chose kings, but there were technically 12 choices left to choose from. And now, for the 2 of a kind, I only need 2 of those kings. But there are 4 kings to choose from. This chooses the 2 cards. This is just a small snippet of an introduction that we are going to spend a bit more time with in regards to probability. What I'm doing right now in my calculator is I'm very quickly typing in these 4 calculations, because for a full house, you got to get 3 of a kind. So we got to choose the kind of card we're going to get, and then the 3 of the 4 cards. And then we have to choose the second kind of card. And then we have to choose 2 of those 4 cards for a full house. I'm saying and very obnoxiously because what do I have to do with all four of those calculations? Yeah, and look what I did right here. Chapow. There are 3,744 ways to calculate, or I'm sorry, or to get a full house in a game of poker. There are 3,744 ways to get a full house in a game of poker. We're going to talk more about poker and probability trees. Oh, that's me. On Friday. Bless you. Hope everyone turn your PJs out inside out tonight. Right? That's the bell. No. No. Because I wear this to bed. Yeah. I know, right? All right. She said she didn't expect that number to be so big, but yeah, it is. All right. Bye-bye. We'll talk more on Friday. Like messing around.